Hi, I'm Tuukka. I will talk about fast FPT approximation of Branchwidth, which is a joint work with Fedor Fomin. So in this work, we give a framework for designing FPT-Approximation algorithms in the general setting of branchwidth of symmetric submodular functions. And we give two applications of our framework. So first, we show that there is a two approximation algorithm for computing the graph parameter rank width and associated rank decomposition with time complexity quadratic in n, the number of vertices, and double exponential in k, the rank width of the graph. And another application is a two approximation algorithm for computing the graph parameter branch width with time complexity linear in n, the number of vertices, and single exponential in k, the branch width of the graph. And this rank width algorithm has some interesting implications, so I will first talk a bit about them. So rank width is a graph parameter that intuitively measures how a graph can be decomposed by cuts of low rank. So here, low rank cut means that the edges going across the cut can be described by a low rank matrix. And rank width it's generalization of the more well-known parameter tree width, in the sense that rank width is always at most tree width plus 1. But unlike tree width, which is always large for dense graphs, rank width can be small also in dense graphs. So it's like in tree width, we want to decompose a graph by small cuts, but for rank width, the cuts can be large as long as they're just going across can be described as a low rank matrix. So examples of graph classes that can be dense but have a bounded rank width are clicks, code graphs, distance-related direct graphs, k-leaf bars. And in this picture, it is a code graph, so it has rank width 1. Rank width was introduced by Ohm and Seymour in 2006 to approximate another graph parameter, click width. So they showed that the rank width and click width can be bounded as functions of each other. So rank width is at most click width, which is at most to the rank width plus 1. And then they gave a three approximation algorithm for rank width with running time f of k, where k is the rank width times n to the 9 log n, which also by this relation gives some approximation for click width as a function of the click width. And why they were interested in approximating click width was that there is this Kurzele's theorem for click width given by Kurzele, Mankowski, and Rotix in year 2000. So they showed that given a graph with click width decomposition of constant width, any MSO1 definable problem like tree coloring or maximum independent set or minimum dominating set can be solved in polynomial time. However, before Ohm and Seymour, it was not known if I give you a graph with bounded click width, how to actually construct this decomposition of bounded width. So Ohm and Seymour showed that you can use rank width, and they gave approximation algorithm for rank width. So they made this Kurzele's theorem constructive in the sense that you could apply it for any graph of bounded click width. However, their algorithm, this dependency on n was quite high. It was like n to the 9 log n, but it was improved quite quickly. So in 2000, Ohm gave a tree approximation algorithm, time complexity f of k times n cube, and then Lilny and Ohm gave actually very soon an exact algorithm also with the cubic time complexity. But after that, there was no improvements in this polynomial dependency until this work. So in this work we give f of k times n square approximation algorithm for rank width, which then implies that this Kurzweil's theorem for rank width and click width can be made constructive in quadratic time. So we have that. So now using this our tree approximation algorithm, we have that given a graph of rank width k, any MSO1 dependent problem can be solved in time f of k times n square. And you can see, because the inputs can be dense graphs, this is optimal as a function of n, but maybe it could be improved if you introduce a function of number of edges. But yeah. So then, before going to our framework, let's review some definitions. So our framework is about branch width of connectivity functions. And so what is a connectivity function? It's a function f from the set of subsets of a set V to integers. And that satisfies two properties. So it has to be symmetric and submodal. So what symmetric means is that for any set A, the value of this function must be the same on A and A bar, where A bar denotes like the complement of A. And submodality, well, it says that you have to satisfy this for any subset AB, you have to satisfy this inequality. Okay, so a connectivity function is some function like this that satisfies both of these. And the branch decomposition of function is a cubic tree, so all internal nodes have degree 3, whose leaves are the elements of this set V. So for example, when we have V's like A, B, C, D, E, F, G, H, this can be one branch decomposition of such a function. And in the branch decomposition, if you have some edge there, so like here it's UV, the width of this edge is defined by the value of this function on the leaves on either side of the cut given by this edge. So it's like this edge corresponds to some partition of these leaves. And now you can see, like, because of this symmetric property, the value of this function is the same on both sides. So this gives you some value of this cut given by this edge. And the width of this decomposition is the maximum width of an edge in this decomposition. And the branch width of this function is the minimum width of a branch decomposition of this function. And some examples are, well, first, just the branch width of a graph. So here we have that this set V is the set of edges of the graph, and we have that this value of this function, it's the number of vertices that are incident to edges in both A and A bar. So it's like A is some set of edges and A bar is some set of edges, and now you look at the vertices that are adjacent to both of them. Okay. And then how the rank width is defined is, for rank width we have this set V is the set of vertices of the graph, and the value of this function is the GF2 rank of the matrix representing edges going across this cut given by A and A bar. So it's like you can see the edges as like A times A bar matrix, where you have like 1 if you have an edge and 0 if you don't have. Then you can compute GF2 rank of this matrix. Okay. And then there are some other width parameters that you can define like this, like carving width, Matroid branch width, and rank width over different fields. Okay, then let's go to our framework. So a framework is for obtaining two approximation compression algorithms with time complexity f of k times n, so linear time for fixed k. And so what this compression algorithm means is that we are given a branch decomposition T of width k. So k is the width of some input branch decomposition, and a compression algorithm either outputs a branch decomposition of smaller width, so width less than k, or concludes that this given branch decomposition was already a two approximation. Okay, so our framework is for obtaining this type of algorithms. And specifically, so for rank width, we obtain this linear time for fixed k compression algorithm, where this input and output decompositions, they need to be what we call augmented rank decomposition, which just means that for every cut, these representatives of equivalence classes of vertices across the cut are stored. And then with this type of compression algorithm, we just apply it n times, like adding one vertex at a time to get like a quadratic time algorithm for fixed k. And for graph branch width, we also get like a linear time compression algorithm, which then actually like the resulting algorithm is also linear time, because we can use it with like 3-bit approximation to start with the branch decomposition of width like 3 times branch width, so we have to apply this algorithm only k times instead of n times. Okay. So now let's go to even more details. So so the setting is the input is this branch decomposition T of width k, which we want to either improve or to say it's a two approximation. And the comparator result of our framework is that we say that the edge UV of this decomposition is heavy if the width of this edge is the same as the width of this decomposition. So this edge is an edge that actually causes the width of this decomposition. So any decomposition has like at least one heavy edge, but can have like n heavy edges. And we show that if this width of this given decomposition is more than 2 times branch width of this function, then a specific refinement operation, which I will define in the next slide, can be applied, which decreases the number of heavy edges and does not increase the width of the decomposition. So it's like by applying one refinement operation, we get rid of at least one heavy edge. And you can see like at the start, we have at most n heavy edges, and we apply like n refinement operations, we get rid of all heavy edges, and then the width of this decomposition must decrease. Okay. So this is like outline of what will happen. And then the algorithmic result is that if we have some branch decomposition that allows to do dynamic programming in time t of k per node. So it's like for fixed k, we can store some constant number of information per node to compute certain partitions of this V, satisfying certain properties. Then we can actually implement a sequence of refinement operations, so sequence that can have like n refinement operations that either improve the width or conclude that it's to approximation in time that is linear in the number of vertices or like number of elements. Okay, so this is so it's non-trivial here that this is actually linear, like instead of quadratic, and it's a bit surprising because there can be like n of these refinement operations. And so, and this T of k is it's what gives this dependence on k. Like for rank width, this T of k is double exponential, and for branch width it's single exponential. So then let's go to this refinement operation. So this refinement operation, it is specified by a four tuple UV, C1, C2, C3, where UV is an edge of this branch decomposition, and this C1, C2, C3 is tripartition of our Cron set V. It can actually be also a bipartition, so one of these can be actually empty also. And let's define this by an example. So let's consider this branch decomposition, and let's say that the edge UV is here in the middle, and this tripartition is the partition into this blue, green, and red elements. So what happens first is that we take 3 copies of a branch decomposition, and but for each copy we keep only the leaves from the corresponding part of the partition. So here we keep only blue, here only green, and here only red leaves. And then we have these edges corresponding to UV in each of these, and we subdivide them. So we add a new vertex W here in the middle. And then what we do, we merge these 3 branch decompositions to obtain one branch decomposition, and like prune these non-labeled leaves away. So now it's like the blue elements live here, the green elements live here, and the red elements live here. Okay, so that is the definition of this operation. It doesn't yet tell anything about if it's useful or not. Yeah, so here's again same example. So our first computational theorem is that if you have some edge UV whose width is larger than the branch width of this function, then there exists some partition C1, C2, C3, so that refining with this edge and this partition actually locally improves this branch decomposition. And what locally improves here means is that in this refined decomposition, all the edges here near the center, so like these 3 center edges, and these edges like distance 1 away from them, also will have width strictly smaller than this ordinary edge UV here. So it's like here we have this heavy edge on the center, and here's like on the center we get rid of all heavy edges. But this doesn't yet tell that this operation is useful. But then what we show, and what is actually like the most technical part of this work, is that actually if there exists some refinement that locally improves our decomposition, then actually if in this refinement we select this partition C1, C2 according to some certain criteria, then this refinement actually globally improves our branch decomposition. So so this is like this decreases the number of heavy edges and doesn't increase width. So this is like the refinement operation that we actually want. Okay, and we actually prove it in 2 parts. So like first that there's local improvement, and then that local improvement implies global improvement. Okay, so then this gives some quite directly some algorithm for approximating branch width. So let's say we have some branch decomposition of width k, and we select some edge, heavy edge that causes this width. So now we root this decomposition on this edge, and denote by this the cut. And and now what we can do, we can use dynamic programming on this decomposition to find actually this partition that we proved that existed, that it's like optimized for all these criteria that allows like global improvement of this decomposition, or to say that it doesn't exist and conclude that actually k was smaller than 2 times branch width of this function. And then if we conclude this, then we return this, and if we find this, then we can use this partition refine our decomposition, so decrease the number of heavy edges. And then we just repeat these steps 1 to 4 until we decrease the width of our decomposition or conclude this here. And this takes at most n iterations. So now you can see like there is n iterations, and it's quite believable that you can do this time programming like linear time, and also like implement this refinement in linear time, but still it's only quadratic in n, because you have to do this over and over n times. Okay, so this is too slow. So our goal is to be linear time in the number of elements. Yeah. So to get the linear time algorithm, let's again look at this same example. And now let's introduce some notation. So let's consider this decomposition rooted at our node UV, this not node, but the edge UV we are using in refinement, and denote by T UVX. So here's node X, the leaves that are below X, so in the subtree of X. So here's like, we have a B here below, and here we have like EF. Now we have that if this, what is here below, if it's a subset of some of this parts C, so here now like this AB, it's a subset of C1, then this refinement actually, it doesn't do anything for the subtree below X. Okay, so what happens in the refinement is actually this subtree gets identically copied to our resulting decomposition. And how we use this is that if this happens, then it's like we have been doing some dynamic programming here. We just directly copy like all information in this subtree. So we copy this dynamic programming information and everything. We don't touch this subtree when we are doing this refinement at all. We just copy it by like changing this parent pointer in our data structure representing this decomposition. So it's like for this we don't have to do anything. And okay. And then for the other nodes for which this does not happen, so which are actually splitted by this refinement, let's call them the edit set R. So here the edit set is this green nodes, these 4 green nodes. Yeah. So what we can do, we can actually implement this refinement operation by changing only this edit set R in time that is linear in the size of this R. So we can just compute this dynamic programming again only for these nodes. And then another thing we show is that over any sequence of refinements, actually the sum of the size of these edit sets, it amortizes to n times single exponential n k. So it's somehow like if you split some subtree, then you are going to actually decrease some potential function quite a lot. And yeah, and what this allows is for us to do everything by like walking over this decomposition, maintaining this dynamic programming, and whenever we have this heavy edge, we use this operation, and it costs only this much, which amortizes to like linear time. Yeah, so this is the main idea of this linear time algorithm. And yeah, that was everything. So thanks for watching. You can find the paper here and the slides and here.